Derivative as a function. Derivative of f of x. So far, we have been able to find the numerical derivative at a point, or the slope of the tangent line at a given point. Therefore, our answer was a number. We now explore the derivative as a function that will allow us to find the derivative at any x equals a value, where the function f of x is differentiable. Let's take a look at the derivative of f of x. So the derivative of a function f is the limit of a difference quotient. This should look very familiar. F prime of x is equal to the limit as h approaches 0 of the quotient f of x plus h minus f of x all over h. So this is very similar to finding the numerical derivative at a point, but instead of letting x equal a particular numerical value, we're going to leave it as the variable x. And we say that a function f of x is differentiable on some interval from a to b if f prime of x exists, so if this limit of a difference quotient exists for all x values in that open interval from a to b. Let's jump right into an example. Here we're given f of x equals 3x squared plus 2x. In part A, we're asked to find f prime of x using the derivative definition, so f prime of x being the limit of a difference quotient. Quick note, if you've taken calculus before, you may know that there is a shortcut to finding the derivative of this function, but here we are explicitly being asked to use the derivative definition. So let's go ahead and get started on that. So we have f prime of x is equal to the limit as h approaches 0 of, so now here we're going to take a look at the top of the difference quotient, starting with the top left part, f of x plus h. So this part right here, f of x plus h, means that we're going to replace each x in the original function with the quantity x plus h. We're doing a composition here. I'm replacing x with x plus h. And that's the top left of the limit of a difference quotient. So we have 3 times x plus h squared plus 2 times x plus h. Again, I was replacing each x here with x plus h. And now I'm done with the top left part of the difference quotient. Then we have minus the top right part of the difference quotient is simply f of x. It's just the function, and that's it. So we don't do anything to it. We just copy 3x squared plus 2x. Because it's a binomial, it has two terms. This minus means that it's going to distribute into each one. So I either distribute right away or I make sure to use parentheses. So this is minus f of x, and then just all over h. Once we've set up the limit of a difference quotient from here, it's a lot of algebra and simplifying, because ultimately we are trying to cancel the h in the denominator, but we have to simplify this numerator here. And it's a lot of multiplying out. X plus h squared, we want to be careful. This exponent does not distribute, because we have to think about this as x plus h times x plus h. So let's jump to it. Let's do the limit as h approaches 0. Still going to have a pretty big fraction bar here. So x plus h times x plus h, if you distribute it all out, I'll leave the 3 in the front for now. I'm going to get x squared plus 2xh plus h squared. So that's just x times x times h, another x times h, and h squared. This 2 will distribute in. This 3 will distribute in as well. But for now, let's just do the 2. So we have plus 2x plus 2h. And as I mentioned before, this minus is going to distribute here and here. So we're going to have minus 3x squared minus 2x all over h. And so, as I said, this 3 is going to distribute, so I can go ahead and maybe squeeze that up here. I have 3x squared plus 6xh plus 3h squared. So that's distributing 3h squared. That's distributing the 3 into each of these terms here, because what I'm trying to do, if I've done everything correctly, in the numerator, all the terms that don't involve h should cancel out. So they do. I have a 3x squared minus 3x squared. Those are opposites. So they cancel out and give us 0. And then I have plus 2x minus 2x. All right, well, those cancel out and just go ahead and give us 0. So in the numerator, what I have left is only terms that are involving h. And I need that to happen because I'm going to factor out at this point that h that they all have in common so that I can cancel it with this h in the denominator. So right now, a common mistake is that maybe students just see this 2h and just like slash out this h and slash out this h and say that they cancel. Unfortunately, they don't cancel because these are terms that are added or subtracted. They're not factors. I can only cancel those factors. So I have to take the h out of there. So the next step here is the limit as h approaches 0 of, I'm going to factor out that h on the top. I'm left with a 6x plus 3h plus 2. So if I take this h out, one of these h's out, and this h out here, this is what I'm left with, and then all over h. So now, only now that I have factored out the h, does it cancel with the h on the bottom. Because when we say cancel, what's really happening is h divided by h is just 1. So that's why they cancel out, right? They just become 1. And so at this point, if I'm evaluating this limit as h approaches 0, well, that means that if I substitute 0 into this h that's left over there, make it look more like an h, then all I have left is 6x plus 2. So now, make some space here, I end up with 6x plus 2. So again, as h approaches 0, the 3h term is gone, and all I have left is 6x plus 2. Now previously, we had only done numerical derivatives. So our answer to the derivative at a particular number was a number, was a numerical value. But now we're considering the derivative as a function. So if we follow this path of equality here, we found out that the derivative as a function of x, f prime of x, is equal to 6x plus 2. So let's summarize that work here. F prime of x, so there's that prime notation, f prime of x is equal to 6x plus 2. Now let's move on to part B of this example. In part B, we're asked to then find an equation of the tangent line to f of x at x equals -2. So anytime we want to find an equation of a tangent line, we are going to need two things. We are going to need the slope at that particular point, and we're going to need the coordinate point. So what do we have so far? We have the x value of the coordinate point. I have x equals -2. So I have -2, I have the x value. Now how do I find the y value that corresponds to that x value? Well, I substitute in -2 into the original function. So this is an x value. I want to get out a corresponding y value, or y is equal to f of x. So here, if I plug in a -2, we'll do that work on the side, f of -2 is 3 times -2 squared plus 2 times -2. So we're looking at 3 times 4 minus 4. So 12 minus 4. So we're looking at the coordinate point being -2, 8. So we have half of what we need. We have a point, xy, negative 2, 8, and we need a slope. Well, in part A, we found the derivative as a function. We found that f prime of x was equal to 6x plus 2. Now, is that a slope? No, it's not. A slope is a numerical value. A slope is a number. But what this is this is a slope function. This function spits out slopes when you plug in different x values. Well, lucky for us, we have a specific x value. We have the x value negative 2. So to find the slope, we're going to plug negative 2 into our derivative function. So we want f prime of negative 2. So that's 6 times negative 2 plus 2. And so that's negative 12 plus 2, or negative 10. Now I have a slope. Right? A slope is a number. So when I have my slope, that's my m value, and I have my point, that's my xy value, or my x1, y1 value, because where we're going to go from here is we're going to plug x1, y1, and m into point slope form of a line. So we know y minus y1 equals m times x minus x1 is the equation for a line in point slope form. So let's go ahead and just plug in our information. So we have y minus 8 equals negative 10, and then x minus negative 2 is x plus 2. So plug in y1, plug in m, plug in x1, and this is our equation of the tangent line. Now this is an equation in point slope form, which for this particular problem is fine because the problem didn't tell me specifically how to leave my answer. So I could leave my answer like this in point slope form. However, if the problem did ask for an equation of a tangent line in slope intercept form, now I have to do a little bit more work. I have to write it in the form y equals mx plus b. So that's just solving for y here. So that would be, distributing in this negative 10. So I'd get negative 10x, and then negative 10 times 2 is negative 20, but if I add the 8 to the other side, it's going to be minus 12. So this would be the answer in slope intercept form. For this problem, either are acceptable, but if the question stated it wanted a particular form of a line, then we'd want to be careful about how we write our answer. Before we go any further, we're just going to take a moment to review some derivative notation, get familiar with it, and how to read it. So here, let y equal f of x be a function, and a be a constant. So here, if we're talking about a derivative, we might see this notation read out loud as f prime of x, and we might have a number instead of a variable x, and that would be read as f prime of a, whatever that number is. We could also see y prime or y prime of a, and all of these first four are called prime notation, but we also have an alternate notation. There's actually quite a few derivative notations, but these are the most common ones that we're going to see in this class. So here, this notation here that looks like d over dx, the way that we read this is that d on the top is like telling us take the derivative. So take the derivative of whatever comes after it, so in this case y, so the derivative of y, and then what's on the bottom here, this dx, is telling us treat x as the variable. So the way that we say that is with respect to x. So take the derivative of y with respect to x. So you might hear it as d dx of y. This is the formal way to say it, the derivative of y with respect to x. You can also see it written a little bit more shorthand, where the y is kind of moved up there next to that d. So we have dy over dx, right? dy over dx. So right here, this d dx part is an operator telling you to take the derivative of this function y here. But when it's all put together like this, dy over dx, that is a derivative. We'll get into that a little bit more in a second. But this is, again, alternate notation for a derivative. And if we want to use that notation but indicate that we're taking the derivative at a specific number, what you're going to see after the dy over dx is this bar here. And that's take the derivative of y with respect to x at x equals a. So you have this big bar that reads at, and then at x equals some particular number. So to be clear, all of these are equivalent notation. So given y equals f of x, we could see f prime of x, y prime, d dx of y, dy dx, or even d dx of f of x. So all of these are equivalent notations, but there are other forms of derivative notation. So as a quick note, when the independent variable is time t, as opposed to it's typically x, like f prime of x, but when the independent variable is time, usually indicated by t, you will also see a derivative represented as a dot. So you'll see s dot t, or simply s dot. And this is often used in physics and engineering. To sort of wrap up this conversation about notation, I really want to focus on understanding the notation in particular of d dx versus dy dx, and really emphasize that they are not the same. And a lot of this just sort of comes with practice. Mathematics is its own language, and we really want to be careful with the way that we use the terms and the notation, because they do mean different things. So to really clarify here, d dx is an operator. It's instructing us to do something. It instructs you to take the derivative and treat x as the variable. So take the derivative of whatever is behind it. So this d dx really doesn't make sense on its own. So by itself, it should not be thought of as a fraction or as itself a derivative. Really, it's kind of a nothing. What I like to compare it to is another operator that you might be more familiar with because of a lot of practice, which is this symbol here, the square root symbol. By itself, it doesn't mean anything, right? It needs something underneath it in order for it to mean something. And it's an operator in that it tells you to do something once I put something underneath it. So it tells you to think about what number times itself gives us 9, right? Find the square root. So it is an operator. It's telling us to do something to this number underneath it. But we typically don't have trouble with that because we've just seen it a lot. It comes with practice. So if you've never taken calculus before, it might be kind of tricky to understand the difference between d dx and dy dx. But I really like you to go back and think about the square root symbol and how that is an operator that's instructing you to do something. As opposed to dy dx is the derivative of the function y equals f of x with respect to the variable x. So now that's the answer. So d dx of y, right, there's something behind it, is equal to dy dx, right? And again, because of that string of equalities, this is also equal to f prime of x. It is a derivative function, right? But d dx is an operator. It's telling you to do something, but do something to whatever comes after it. Right? So by itself, it doesn't really mean anything. Let's take a look at another example. Here, we're told to find the derivative of -2 over x with respect to x. Here, we are going to use the limit of a difference quotient to find the derivative. So we'll set this up. The derivative of this function with respect to x equals the limit as h approaches 0 of that difference quotient, where f of x plus h goes in the top left corner. So this is going to have to be f of x plus h. Well, there's only one x in the function, so we're going to replace that x with x plus h. So we have negative 2 over x plus h. And then the difference quotient continues with minus f of x. So just minus the function itself. And that is negative 2 over x. So we're going to have minus negative 2 over x all over h. So we have f of x plus h minus f of x all over h. In the numerator, I have minus a negative, so that's going to end up being a positive. And in order to simplify this, we have a few choices. We can either clear fractions, or we can, in the numerator, combine the two fractions with common denominators. I'm going to go ahead and choose that route. I'm going to combine these two fractions using common denominator. So one denominator is the quantity x plus h. The other is just x. So the least common denominator is x times x plus h. So in our next step here, we'll have the limit as h approaches 0 of, we're going to have that negative 2 over x plus h, and I'm going to put the x I need on the bottom for that common denominator, but if I put an x on the bottom, I also need an x on the top, because x over x is just 1. And then I have plus, I already have a 2 over x, but I need them to have common denominator, so I'm going to have to put an x plus h on the bottom, which means I'm going to need a quantity x plus h on the top, because again, x plus h over x plus h is just 1. So now these have common denominators. They have x times the quantity x plus h, so I can add the two fractions in the numerator together. And then in the denominator, I still have an h. So here's where we're at. We have the limit as h approaches 0 of, let's see, negative 2x plus 2x plus 2h. So what's happening there is I'm distributing in the 2 to the x plus h quantity on the right, and then all over that common denominator of x times x plus h, and then all over h, all over that one h that's on the bottom. So essentially I added across the numerator here because I had common denominators. So I put it all together. Now notice that minus 2x plus 2x equals 0. Those are opposites. And so I have 2h over x times the quantity x plus h all over h. I'm going to make that h over 1. In this next step, I have the limit as h approaches 0. I have 2h over x times x plus h. So that's this 2h right here over x times the quantity x plus h. And then instead of dividing by h over 1, I can multiply by the reciprocal. So times 1 over h. And that's to help us recognize that the h's are going to cancel out. So the h's are going to cancel. And now that I've canceled those h's, they're factors, right? So when we say they cancel here, it's because h over h is just 1. And when I substitute in the 0 into h, because the limit as h approaches 0, what I'm going to be left with is 2 over x times x. So I'm going to have 2 over x times, right, x plus 0. Technically, I'm plugging that 0 into h. So that's 2 over x squared. So if I follow this path of equalities here, here's the conclusion that I arrive at, that the derivative with respect to x of negative 2 over x is 2 over x squared. Positive 2 over x squared. That's what we just found if I follow this path of equalities. Introduction to reading the graph of f of x to find derivatives. We're going to go ahead and focus on the graph of f of x for a moment. If we had the equation of f of x, we know that if the limit of the difference quotient doesn't exist, then the function is non-differentiable. But if we're looking at a graph, how do we know that the function is not differentiable? Well, we would be looking for one of these types of non-differentiability. So a function is not differentiable at all of the following, at what we call cusps, vertical tangents, corners, and any discontinuity. So here's a graphical example of a cusp. We have where these two curves sort of meet up at this sharp turn here. So if we were to think about this as the point A, and we want the slope of the tangent line, well, what's the tangent line? A tangent line informally, just kind of taps the surface and goes through that point. So is it there or, is it there? Basically, it's not unique. So how are we going to find that one slope of a tangent line at that cusp? Well, we can't. So that's why that is a location of non-differentiability there. And the same applies to a corner. So I'm kind of skipping over here for a second. A corner like the absolute value of x function. So right at x equals 0, I have a corner where these two lines meet. So basically any sharp turn, we're going to have that issue of, not having a unique slope of a tangent line. So we say at those values, we are non-differentiable. And then also at a vertical tangent line. So here I have this function, and right at what we're calling this value c, if you were to go to the function and plot that point of tangency and draw a tangent line, well, there is a tangent line, but it's perfectly vertical. And the slope of a vertical line is undefined. So that means that we don't have the slope of the tangent line, which is the derivative. So we're not differentiable at any place where there's a vertical tangent line. And then finally, we can't be differentiable at a place of discontinuity. Well, why not? Because the limit doesn't exist there, right? So we know, again, that given a function, if the limit of a difference quotient doesn't exist, I'm not differentiable. Well, here, at any discontinuity, the limit of a difference quotient doesn't exist. So all the types of discontinuity, jump, removable, infinite, oscillating, if I'm not continuous, then I can't possibly be differentiable because that limit would not exist. Following up from that last piece of information, we know that differentiability implies continuity. So if we're told that a function is differentiable, then it has to be continuous at that point. And we know, because we just talked about it, that if f is discontinuous, then the function is non-differentiable. And it's that idea of the limit of a difference quotient. If that doesn't exist, right, then we don't have continuity. So if we don't have continuity, we don't have differentiability. If we do have differentiability, then we must have continuity, because then that limit of a difference quotient does exist and equal the function value. So the big warning here is that this doesn't go in the opposite direction, what's called the converse. Continuity does not guarantee differentiability. And we just looked at an example of that, which is the absolute value function. So this is a continuous function. I drew it without lifting up my pencil. But right at that sharp turn, I'm not differentiable. So the order matters here. If a function is differentiable, then it's continuous. But a continuous function isn't necessarily differentiable. Let's take a look at an example. Given the graph of f of x, shown here to the left, we want to sketch the graph of its derivative, f prime of x. So as I said, on the left-hand side, this is my graph of f of x, and I want to graph f prime of x. And what I'm going to do is, next to f prime of x, I'm going to write the word slopes. When I graph f prime of x, I want to think about it as graphing the slopes of the original function. right? Because the derivative, after all, is the slope of a tangent line. So just kind of informally next to it, I'm putting slopes. That's what I want to think about. So what I'm going to do is come over here to f of x and recognize that this is a piecewise linear function. It's 3 different pieces and they are all lines, which is nice to start with because we can exactly identify the slope of each of these line segments. Let's start from left to right. On the left side of this graph, this first piece, this first function, has a negative slope since the function is decreasing. And if I pick a point to get to the next point, I'm going to have to go down 1, right 1, down 1, right 1. So the slope of this line segment here is -1. So what I'm going to do is I'm going to go ahead and put -1, -1, -1, -1, just kind of all along that line segment because that's the slope. And then right here at this corner, I have 2 lines meeting. I know that the derivative doesn't exist there, right? That's a place of non-differentiability. So what I'm going to do is label that value, or that at that location, the slope as dne. So the slope doesn't exist there, right? So the derivative doesn't exist there. It's non-differentiable. But right past 0, so 0 is kind of the x value problem location, but right past 0, I'm now on a new line segment where I can identify the slope. And to identify the slope here, it's going to be a positive slope because it's an increasing piece of a function. I'm going to go up 2 units, right 1, up 2, right 1, up 2, right 1. So the slope of this line segment is 2. So next to that entire line segment, I'm going to write 2, 2, 2, 2, just to remind myself that's the slope. Right at the x value 3, I have another corner. So I have another place where these 2 lines meet, and that's a place of non-differentiability. So I'm going to put another dne. But past 3, once I get right past 3, I have a horizontal line. And a horizontal line has slope 0. So across this horizontal line, I'm going to go ahead and put a couple of zeros to indicate my slope. So now, coming over to this blank xy plane over here, my job for graphing f prime of x is graphing the slopes on the original function. Well, from -infinity all the way up to 0, the slope is -1. So over here, from -infinity all the way up to that x value 0, I want to indicate a slope of -1. It's just constantly -1. So it's going to be a constant function along -1. So I'm going to go ahead and draw that horizontal line. All right, I'll draw a little arrow. And then right at the x value 0, so here this is the x value 0, right at the x value 0, I know that the derivative doesn't exist. So I don't want an actual point along the line at x equals 0. I'm going to put a big circle there to indicate that there is no slope there, right? There is no value. So I just want to make it really clear by putting a big, empty circle there. This isn't an empty circle. This is the number 0, to be clear, right? This is the origin, it's 0. All right, so now let's indicate the slopes on the next line segment. So between the x value 0 and the x value 3, right, 1, 2, 3, I have slopes of 2 constantly, so from 0 to 3. So this next little line segment is going to be horizontal. And again, right at 0, I'm going to put an open circle just to really indicate there's nothing there, right? There's nothing there. So what this is saying is that at the x value 0, if I try to determine, well, what's the slope? There is no slope, right? There's no slope of a tangent line right at the x value 0. I'm going to go ahead and make this black just to really indicate that it's the number 0 and not an open circle. All right, and the same thing applies at 3. At 3, we said the derivative doesn't exist, which means there's no slope of a tangent line. So if there's no slope of a tangent line there, I want to make sure and be really obvious that right there at 3, there's no actual point there, right? And then beyond 3, the slope is just 0, right? This arrow, it's going on forever. So beyond 3, the slope is 0, which means it's on the x-axis. So right at 3, there is no slope of a tangent line. Whoops. And then beyond 3, right beyond 3 and forever onward, the slope is 0. So this is my slopes graph. This is my derivative function. So when I look at this derivative function, let's say I go to the x value 1. At the x value 1, I find the function is at 2. So that tells me that on the original graph, that at the x value 1, when I go up and I find the function, it's going to have a slope of 2 there. And look at, if I go over here to the original function, I go to 1, I go up to the function, it has a slope of 2. It's not the output, it's the slope. Because the same thing applies at the x value 2. If I go to the x value 2, the y value here is 2, meaning the slope is 2. So here at 2, I go up and find the function, the slope is 2. Let's continue on thinking about the graphical interpretations of derivatives given the original function f of x. But now, instead of having a function that's just a bunch of lines, we're primarily going to deal with functions that are curves. So here, on this example, this downward facing parabola, looks like a parabola anyways, that's our function f of x. So it is not a bunch of straight lines, it's a curve. So how do we interpret the original function f of x and think about derivatives given that original function f of x? Well, we still think about slopes, but now we actually need to construct the tangent lines. So if I pick some point here on the left side and I draw myself a tangent line, that slope is a positive slope. So from left to right, it's increasing. And a positive slope on f would mean that f prime, the derivative, is above the x-axis. So whenever I have a positive slope tangent line on the original function, then the derivative graph, the slopes graph, is going to live above the x-axis. Now right at the very top here, if that's the point of tangency, and I draw a tangent line, the slope is 0. So a 0 slope on the original function would mean that on f prime, I'm on the x-axis. So whenever I have a 0 slope, whenever I have a horizontal tangent line, then the derivative would be on the x-axis. I would have an x-intercept. And then on this right-hand side over here, if I were to draw a tangent line at this point of tangency, the tangent line would have a negative slope. A negative slope on f would mean that f prime, the derivative, needs to be below the x-axis. So here, this is just kind of a way to, again, interpret the graph of derivatives given f of x. So let's apply it to a matching example. In this example, we want to match the functions top row with their derivatives in the bottom row. So across the top here, we have 4 different functions. Let's go ahead and give them different names. I'm going to call this first one f of x, this one g of x, this one h of x, and I'm going to call this one p of x. Just don't want to use a vowel. All right, so now these are the original functions, and we want to take a moment to analyze their slopes. Well, this first function is linear, and so we can identify its slope exactly at every x value. So the slope would be just 1, because we're looking at up 1 over 1, up 1 over 1, up 1 over 1. So we have just a line that passes through the origin, but with slope 1 everywhere. So 1, 1, 1, 1, 1, 1. And so if I want to match that with a function on the bottom that is its derivative that indicates that the slope is always 1, well, if the slope is constantly 1, I'm looking for a function that is constant along the y value 1, which is this third graph here. So at this y value 1, I can see this perfectly horizontal line. So this third graph would be the graph of f prime of x. Now the second graph is now a little bit more interesting because it's not linear. It's a curve. It's a parabola. And what I can do here is I can start from left to right and just start thinking about those slopes of tangent lines. And I'm not necessarily going to find those slopes exactly because I really can't from the graph, but I at least want to know whether those slopes are positive or negative as a way to help me start to do this matching process. So over here on the left, if I were to draw a little tangent line, I would have a negative slope. And then if I go a little further, I have another negative slope. If I go a little further, I have another negative slope. So I'm just drawing little tangent lines. Those lines all have negative slope. Until I get to the very bottom of the parabola. And at the very bottom there, if I draw a tangent line, now that slope is 0. And then, once I get to the right-hand side, once I get on the right side of the y-axis there, if I start to draw some tangent lines, those all have positive slope. And I can be very observant and notice that the slope is getting steeper. So they're all positive on the right-hand side, but this tangent line up here has a very, very steep slope, so a really big number for slopes as I continue on. But just this analysis here is going to be enough to help us match to one of these remaining functions for the derivative. And so what we're looking for is a graph where on the left side of the y-axis, so anytime I was on the left side of the y-axis, I have negative slopes. So what I'm looking for is a graph on the bottom here, where on the left side of the y-axis, my derivative graph is negative, is below the x-axis. So if I look at this first option here, it's a good candidate. So on the left side of the y-axis, the function is below the x-axis. The function is negative. So that part checks out. Well, what about right at the x value 0? Right at the x value 0, the tangent line, the slope of the tangent line is 0. I had a horizontal tangent line with a slope of 0. So that means on my derivative graph, I better be on the x-axis. I better have an x-intercept at 0. Well, this first graph, again, is looking pretty good because I have 0, 0 as a point on the derivative. And then once I get to the right side, once I get on the other side of the y-axis, from value 0 onward, I have positive slope. And notice, I have positive slope that's getting bigger and bigger. I have steeper and steeper slopes. And so as I go to the right, once I get to the right of 0, those slopes keep getting bigger and bigger. The outputs are bigger and bigger. So this graph here is the graph of g prime of x. And if I look at my other options, those definitely didn't work. On the left side of the y-axis, I have positive slopes. I'm above the x-axis here. On this one, same thing. On the left side of the y-axis, I have positive slopes. So this is the graph of g prime of x. Now moving on to the third original function here, which I've called h of x. So what we can absolutely do is we can start from left to right and we can just think about those slopes, right? And indicate whether they're positive, 0, or negative. But another technique that we really want to go to right away, it's really going to help narrow it down when it's a matching problem, is instead of just going from left to right, it's looking at the original function and going straight for those horizontal tangent line locations. And especially recognizing just how many horizontal tangent lines there will be. So on this graph, there are 2 horizontal tangent line locations. So 2 little, peaks and valleys there. So here and here, I have one little peak where the slope of the tangent line would be 0, and one little valley where the slope of the tangent line would be 0, right? And they're not corners or cusps, right? They're nice smooth curves where the tangent line is perfectly horizontal and with a slope of 0. So if we're trying to match, right? If we're trying to match, what we're looking for is a derivative graph that has 2 x-intercepts, because that's where the slope is 0 on the x-axis. The derivative would have to be on the x-axis. Well, looking over here at this derivative possibility, this graph has 2 x-intercepts, right here and right here, as opposed to this last one has 3 x-intercepts, here, here, and here. So it's looking like this second one is h prime of x is the derivative of that third function. And that is correct. We can just narrow it down based on that alone. We can also confirm a little further by recognizing that over here, the slopes would be positive. So I'd be above the x-axis. And then in between those two x-intercepts, I would have negative slope there, right? I have a little negative slope. And then once I'm on the right side of that horizontal tangent line, slopes over here are going to be positive. So above the x-axis again. So I'm positive, right, above the x-axis, and then below the x-axis, and then above the x-axis again. So this h of x matches with this h prime of x here. And then finally, of course, there's only two left. So we know that those are going to go together. This is p of x, and this is p prime of x. But let's just confirm, especially with those horizontal tangent lines again. So we know that there are 3 horizontal tangent lines on this last graph. So 3 places, right, where that tangent line is perfectly horizontal. So we can see very nicely how they line up, right, exactly with those corresponding x values. So at -1, 0, and 1, I can see those are the 3 x-intercepts on p prime of x. And everything else checks out, where the slope here is positive anywhere on this side. Then I have negative. Here I have positive. And over here I have negative. So I'm above the x-axis. I'll indicate any above the x-axis parts with yellow. Right? So I'm above the x-axis from -infinity to -1. And then from 0 to 1, where I have that positive slope. So it corresponds to these parts right here. Right? Anywhere I have positive slope is where I'm going to be above the x-axis on the derivative graph. So one of the last things that I'll just mention here is that these definitely take practice, and what I'm really going to encourage you to do is to not base your answers for matching like on how it looks, quote unquote. Just so sometimes what students do is they're like, oh, this U shape looks like this U shape. It has nothing to do with that, right? So we want to very closely analyze the original function and think about its slopes. And then once we've analyzed the slopes, then go ahead and look at our derivative options in terms of being on the x-axis or above the x-axis. It's not like this one looks like this one. I get a lot of that, especially early on. And so it's just something that I want to encourage you to avoid. And mark up your original functions as much as you need to really analyze those slopes.